We've spent a significant amount of time in the past several videos talking about acids, and now in this section we're going to go on to talking about bases. In this first video of chapter 7.6, we'll talk about writing base dissociation reactions and the base dissociation constant. In this problem, we're asked to write the reaction of NH3 with water. So NH3 is reacting with water, and they're going to react at equilibrium with one another to form something, but we don't really know what those products are, and we have to be able to predict what the products should be. So to help us do that, we have to consider whether NH3 is an acid or a base, and we have to think about where we can look to find this information. The table of acids and bases is your guide that helps you to determine that. And when you look on the table of acids and bases, you find NH3 located right here under the A- column. So since NH3 appears in the A- column, that means that NH3 is a base. With that in mind, we can now begin to figure out what the reaction will be between NH3 and water. So NH3 reacts with water, and we now know that NH3 acts only as a base. Now, water, on the other hand, when you go back and look at the table, water can act as either an acid or as a base because it appears in both the HA and the A- column. But because the NH3 is acting as a base, that means that in this reaction, water has to act as an acid. You can't have two bases reacting with one another. So if NH3 is a base, water has to behave as if it were an acid in this reaction. Then we remember what the Bronsted-Lowry definition tells us. It says that bases are proton acceptors, and it says that acids are proton donors. All right, now we should be able to predict the products of this reaction. And because both the NH3 and the water are weak acids and bases, this will be an equilibrium reaction. When the NH3 accepts a proton, or when it gains a proton, it will become NH4, and then it carries a plus charge because it's gained an H+. And for the water, when H2O gives up one of its H+, you're going to be left with the hydroxide ion, OH-. That's the reaction, and that's how we're able to predict the products of the reaction based on our knowledge of Bronsted-Lowry acids and bases. We can generalize this even further and look at what the general reaction of any base would be with water. So for any general base B reacting with water, they'll react at equilibrium because we'll say that both are weak, right? The base is a weak base and water is a weak acid. And what you're going to go on to produce will be BH plus when the base gains a proton. And when the water gives up a proton, you'll be left with the hydroxide ion. Furthermore, we could consider what the equilibrium constant expression would be for this general reaction of a base with water. And when we would write this equilibrium constant expression, we're going to call the equilibrium constant for this reaction K subscript B, and that stands for the base dissociation constant. And the expression for Kb in this general equation would be our product, BH plus, times the other product, hydroxide, over the reactant B, and H2O, remember, right, that's our solvent in this solution. H2O is a liquid, so it does not get included in the Kb expression. And so that's our full expression for Kb. If we were to take a look back at the equilibrium reaction for NH3 in water and write the Kb expression for that, what we would get is that for this reaction, Kb is equal to the concentration of NH4 plus times hydroxide over NH3. Just for the sake of completeness, it's nice to see that and see a specific case in addition to the general case. That brings us to the end of this video, and in our next video, we'll talk about finding the value of Kb.